All right, welcome everybody. So in this video, we are going to continue our work with bases. And in particular, we're gonna formalize a result that you may have been thinking about informally, which is given a vector space V, that there is a unique number of vectors that form a basis for that vector space. So just to recall the definition of a basis for a vector space, we say that a set of vectors B that contains vectors b1, b2, up to bn form a basis for a vector space as long as the vectors in this set B are linearly independent, and secondly, that the span of all of the vectors in this set equals the vector space V itself. So for example, we can take a vector space V, which is not actually column vectors, but consists of polynomials of at most degree 2. That we denote P2. And we're going to use the typical operations of how we add polynomials and how we multiply a polynomial by a scalar. And for this vector space, we've seen that kind of a standard basis would consist of the set that consists of the polynomials 1, t, and t squared. So by taking linear combinations of these three vectors, we can construct any polynomial that has degree at most 2. So this basis consists of 3 elements. And we might want to think, well, is it possible to have a basis with less elements or with more elements? So here's a set of 1, 2, 3 different vectors from our vector space P2, and we might want to think about, well, does this form a basis? This is a basis as well. And so you can kind of check these conditions up top and verify that this gives us another basis, and it also has 3 vectors. If we consider basis B2, that consists of one polynomial of degree 2, 1 minus 2t plus t squared, and a second polynomial, 5 plus t minus t squared. Is this a basis? This has only 2 vectors, and it is not going to satisfy the property that those 2 vectors are going to span all of the vector space V. We need 3 vectors to span all of V. And we can take a look at a basis B3 that in this case consists of 1, 2, 3, 4 different polynomials. And we can ask, is this a basis? And because this basis has 4 elements, you might be suspecting no. And the reason why is this set of vectors B3 are not linearly independent. So if we're going to satisfy both of these conditions 1 and 2, any set that is going to do that for this vector space is going to have to contain 3 different basis elements. And so we'll prove this fact on the next slide. Okay, so we would like to prove that given any vector space, the number of vectors in the basis is unique, is going to be the same. So here we're first going to prove the following theorem, that if we have a vector space V, and we know that we have some basis B that consists of n elements, then any set containing more than n vectors must be linearly dependent. So this is going to tell us that any set that has more than n vectors is not going to be a basis because it won't satisfy the linearly independent property. So for example, in the previous slide, we were thinking about our vector space as P2, polynomials at most degree 2, and we have this standard basis that has 3 elements in it, and we wanted to consider whether some other set that consists of 4 different polynomials could be a basis for P2. So this theorem is going to allow us to rule out this fact that a set with 4 vectors could be a basis, since we already have a set with 3 vectors that we know is a basis. So let's take a look at this proof. So let's consider some other set U that consists of more vectors than our initial basis. So for example, this could be our initial basis with 3 vectors, and here's some other basis that consists of P equals 4 bigger than 3 vectors. So then, since we know that B is a basis for V, we can find B coordinates for each vector in U. So I know that each vector in U can be written as a linear combination of basis vectors in B because I know B spans the entire vector space V. So that means each of these vectors in U we can write as a linear combination of these vectors over here. And this is what we call the B coordinates for these vectors in U. So for example, with our polynomial vector space, we could take one of these basis vectors like 6t plus 2t squared and write them in terms of linear combination of our standard basis, which would be 0, 6, 2. And so now we've got a column vector that has 3 elements, this 3 being the number of basis elements, the number of vectors in our first basis. So now we have a set of vectors S, which is going to consist of each of the basis vectors in our set U that are written with respect to the coordinates for our initial basis B, which we know has n elements. So this set is going to have to form a linearly dependent set in Rn since we have more columns in our matrix, which is equal to P, then we have rows in our matrix, which is equal to n. So if I construct a matrix M out of all of these column vectors, which are the B coordinates for each of the vectors in our alternate set U, then we get this matrix, which is an n by P matrix. And again, we have more columns than we have rows. So at best, I have a pivot here, I have a pivot here, all the way down to having a pivot here. But once I've hit this last row, the nth row, we still have more columns left. And so we're not going to have any additional pivots. We're going to have columns without a pivot. And when that happens, we know that the column vectors of the matrix are linearly dependent. So that tells us that this set of vectors, U1, U2, UP, are linearly dependent, and that's what this theorem was claiming. So to illustrate what's happening with this example for our vector space P2, we can take each of these 4 polynomials in our basis and write them in terms of coordinates relative to this basis B. And then I could take a look at each of these 4 vectors, put them in a matrix, and you could see that this matrix is going to have to have at least one column that does not have a pivot. So these 4 columns that each contain 3 elements has to be linearly dependent. So any set U that has more than n basis elements is not going to be a basis itself because it will be linearly dependent. All right, so now that we've proven the previous theorem, we have what we need to prove the main result here that we've been claiming, and that is if V is a vector space that has a basis of n vectors, then we know that every basis of V also must contain exactly n vectors, that this is a unique number of vectors that we need in a set in order for it to be possibly be a basis. So let's see how we can use the previous theorem to quickly verify this result. So let's say I've got basis B1 for this vector space V, and I know that that has n vectors in it. Then let's consider some other basis or B2 for this vector space. So here what we are assuming is B1 is a vector space with n vectors. B2 is some other basis for V, and let's assume that it has m vectors, and at this point, we don't know anything about the relation between m and n. However, from the previous theorem, since I know that B1 is a basis with n vectors, I know that B2, which is a second basis, can't have more than n vectors. So this tells me that I know that m has to be less than or equal to n. It can't be greater than it. And we can use the same exact logic for B1. Namely, since B2 is a basis with m vectors, then we know that any other basis, namely B1, cannot have more than m vectors. So this tells me that n has to be less than or equal to m. So now that we know m is less than or equal to n, and n is less than or equal to m, that proves that these two numbers have to be the same. And in fact, any basis of vector space V must contain the same number of vectors n.